I'll go through 4 different common probability distributions in engineering, and then I'll show something a little bit about the tabular distribution and give an example of why you might want to use that in probabilistic damage tolerance analysis. So we'll be talking about the normal, log normal, Weibull, and Gumbel distributions for about 10 minutes. So normal distribution is probably the most common distribution everybody is familiar with. It's often used for statistical errors, and it's characterized by just 2 parameters, the mean and the standard deviation. A lot of the material property distributions in PDTA are normal distributions. Shown here is a graph for 2024 aluminum, and you can see it's pretty symmetric and normally distributed. So a symmetric distribution, if you sum multiple normal distributions, you end up with another normal distribution. And we have here the PDF function. There's no integral, no closed form integral of this function. So when I talk about the CDF in a moment, we'll just be using a symbol for that. And it's implemented in softwares, but you can't just write out an equation for this, the CDF of this function. And the graph shows where the 1, 2, and 3 standard deviations from the mean are for a normal distribution. So 68% of values will fall between plus and minus 1 standard deviation. 95% will fall between plus and minus 2 standard deviations, and 99.7 will fall between plus and minus 3 standard deviations. So after that, the tails decay pretty rapidly for normal distribution. Again, the relationship between CDF and PDF is that the PDF is the slope of the CDF, and the CDF is the integral from negative infinity to a particular value of the PDF. So here's the PDF for normal distribution. This is what you would use in Excel, Python, MATLAB, or R to transform variables to and from a uniform distribution, let's say. Calculate probabilities from given values of X. Now, the normal distribution function requires that everything be transformed to a standard normal distribution. That is, normal distribution with a mean of 0 and standard deviation of 1. So the mean is subtracted and then divided by the standard deviation. The inverse transformation, you just take the inverse normal CDF and multiply by the standard deviation at mu. We have a table on each of these for each of these 4 distributions that shows the common parameterization in Excel, Python, MATLAB, and R. You can see that they're all using mu and sigma parameters. But in Excel, you have an extra parameter that's just a Boolean. And that's because the distribution function in Excel is a probability that gives you, by default, probability density. You have to pass true in order for it to give you a cumulative distribution. Also, I won't mention this on every slide, but the packages that you need in Python are SciPy stats and in R stats to access these functions. Next, we talk about log normal distribution. This is closely related to normal distribution. So if the log of the values is normally distributed, then you have your variable is log normally distributed. That means that the values that are not transformed before you take the log, they can't be negative. They have to be positive. This is an unsymmetric distribution with a long right tail. The PDF function is shown here. You can see it's very similar to the normal distribution, just you have an ln of x inside the exponential and an x outside here in the denominator. So again, you can't, in closed form, you can't write an equation for the integral of that. Now the 2 parameters, lambda and zeta, for the exponential distribution are the mean of the log of the values and the mean of the standard deviation of log of the x values. So typically when you have a set of data, you have the data and its mean and its standard deviation. You would have to transform or calculate a zeta and lambda value from those to use with standard softwares like Excel, Python, and the rest. So you have to be careful with the log normal distribution, because it's basically using the standard normal distribution function inside to calculate, CDF and inverse CDF. So here you have the log of the value minus lambda over zeta. That's just transforming your values into standard normal space, and then the standard normal function. And the inverse of that is to multiply the inverse by zeta, add lambda, and then take the exponential of that quantity to get your values back out. Again, all the software uses the lambda and zeta formulation or parameterization. Python has a little bit of a difference where it's expecting a median value. So that's the exponent of the lambda value. Weibull distribution is widely used in engineering, often for fatigue and times of failure. In PDTA, you'll see it used for equivalent initial flaw sizes or initial crack sizes. So shown here is a PDF of some initial crack size data from the T38 wing. There are two parameters to the Weibull distribution: shape and scale. Shape denoted alpha, scale beta. And this is a PDF function that's easy to write, a closed form, and also to integrate and get a closed form CDF. It's not as easy to calculate what the mean and standard deviation of the Weibull distribution are. You have to use the gamma function for that. So you can see several examples of Weibull distribution here. You see with a shape of 1, which you essentially, actually what by definition you have is the exponential distribution. Shape of 2, it starts to move out. It becomes shape of 3. It looks more and more like a normal distribution as the shape increases. So Excel has the Weibull distribution, cumulative distribution, and PDF function built in, but there is no inverse CDF function in Excel. You have to manually input that if you need to use it. So that's given here, just in case somebody's going to write some probabilistic software in Excel. Also, you have the distributions in Python and MATLAB and R. For Python, you have to specify Weibull min, because there's both a Weibull maximum and Weibull minimum. And for MATLAB, you have to reverse the order of the parameters. Last, I'll just go over the Gumbel distribution. So this is an extreme value distribution, which means if you had measured loads throughout flights for several flights, and then you took a distribution of what was the maximum load on each of those flights, you would end up with a extreme value distribution. You can have either a maximum extreme value or a minimum extreme value. For Smart DT, we've implemented it in the loading. And you can see here out of the loads module several different examples of extreme value distributions you get for if you selected the type of flight, the type of mission, we sometimes call it usage, as single engine unpressurized, twin engine unpressurized with used for instructional, and single engine unpressurized used for instruction. You can see, as say for beginner pilots, you have higher loads, higher maneuver loads. So Excel does not implement either the CDF or the inverse CDF for the Gumbel distribution. You can enter those manually. They're closed form equations and easy to do. Python, MATLAB, and R, you generally use what's called a generalized extreme value distribution, and you set the shape of it to 0. So you see the 0 parameter in all of these. And one last note, for R, you have to get a new package. It's not included in the stats module. Now, here's the tabular distribution as we've implemented it in Smart. A lot of softwares will have a tabular distribution input because it's not practical to write inputs for all kinds of distributions. There are probably hundreds of distributions. So what we have here is the format that you would use to create a tabular distribution file in SmartDT. You can put a comment in there to remind you or to note for later what this file was. It just has to start with an exclamation. 2 columns. The left column is your values, the X values, and the right column is the CDF. Now, some softwares will make a assumption about what happens in the tails if you don't define the CDF all the way to 0 or all the way to 1. For SmartDT, you have to define everything down to 0 and 1. It will not make any assumptions for you about what happens if you leave off your probability right here. It just will tell you that you have to define it all the way to 1. And in the software, you can, if you load a tabular distribution, you can plot it as a PDF. So perhaps in the future we'll have the ability to show the CDF or mountain plot, but for now you can see the PDF to check that you got the right distribution in there. Quick example. It's why you might want to use a tabular distribution. Let's say you had a log-normal distribution for your EFIS and you want to add a 1 in 1,000 probability that you have a rogue flaw between 0.03 and 0.05 inches. You can do that by creating a weighted sum of these 2 PDFs. And then you get a user-defined PDF over here. Note that the rogue flaw bump in the tail of that is very difficult to see, or impossible to see. If you zoom in, you can see it if you zoom in the right place. But for tabular distribution, you need the CDF, so you need to integrate this. So what would we get? Here's what the CDF plot looks like. Again, you can't see in the tails what's happening. But if you plot both of these tails on logarithmic scale, so on this side you have probabilities, this side you have exceedances, then you can see that it makes a drastic difference in the CDF from values from 0.999 down. And that's good to know, because in probabilistic damage tolerance analysis, the POF will be sensitive to what happens in the right tail, especially the EFIS distribution. So, I mean, I've had problems that took me a day to debug because I put in a bad EFIS, and basically the tail just went way out in the space, and then it was hard to find. So just that's all for this set.